want you to picture a scenario for a second.
Okay.
You're standing in front of a lathe, and you're tasked with cutting a piece of metal. But it's not just mild steel or aluminum.
Right.
This is the stuff nightmares are made of. The kind of materials used in the hottest part of a jet engine, or maybe the stress-bearing joint of a surgical implant.
Yeah, the really high-stakes stuff.
Exactly. Now, if I asked you what determines whether your cutting tool survives that cut or just shatters into 1,000 pieces, what's your gut reaction?
I mean, for the vast majority of people, and even plenty of engineers early in their careers, the answer is almost always hardness.
Right. It feels intuitive.
It does. If I want to scratch glass, I use a diamond. It's a contest of substance. Like, my material just needs to be tougher than your material.
It feels like a simple brute force equation.
Exactly.
But this deep dive is going to challenge that entirely. We're looking at a report today on optimizing ISCAR insert geometry. And the takeaway is, honestly, pretty radical.
It really is.
Because it argues that while the substance, the carbide grade matters, the real difference between success and catastrophic failure isn't the material itself, it's the shape.
It is entirely about geometry.
Oh.
And we aren't talking about the shape of the part you're making, right? We're talking about the microscopic architecture of the cutting edge itself.
Right.
We are diving into the invisible physics of the tool workpiece interface.
Which sounds very sci-fi.
It kind of is. It's a battle against heat, pressure, friction. And surprisingly, the way to win isn't usually just to be stronger. It's to be smarter about the angles.
So our mission today is to unpack how ISCAR engineers use pure geometry to basically cut the uncuttable.
Let's do it.
But before we get to the solutions, I think we have to respect the villains of this story. The report groups them under the label difficult to cut materials.
Yes.
Which feels like a really polite way of saying tool killers.
It's a very diplomatic label, yeah. In the manufacturing world, these are the antagonists that literally keep machinists up at night.
The bad guys.
Right. We're talking about things like stainless steels, heat-resistant superalloys. You'll see those called HRSA, titanium alloys, hardened steels, and abrasive cast irons.
A complete rogues gallery of metallurgy.
Exactly.
And the report makes it super clear that these aren't just hard materials. Because if they were just hard...
We just use harder tools and be done with it.
Right. The issue is that they have distinct personalities and they all misbehave in totally different ways.
They fight back. That's the best way to put it. Take work hardening, for instance.
Oh, I wanted to ask about that.
Yeah, we know materials like titanium or certain stainless steels are prone to this. You hit them with a cutting tool, and the heat and the pressure actually change the microstructure of the metal right in front of the cut.
It literally changes the metal.
Yes, making it harder than the material behind it.
I've always found that concept fascinating. The idea that the metal kind of armors itself the moment you try to cut it.
It's a survival mechanism for the metal.
But I didn't realize how much geometry dictates that. I just assumed managing work hardening was about, keeping the coolant running so it doesn't get hot.
I mean, coolant helps, definitely, but geometry is the driver. Imagine you're trying to slice a loaf of bread that turns to stone the slower you cut it.
Okay, weird bread, but I'm with you.
Right. If your knife is dull, or if the geometry is what we call negative business, you're pushing the material. You're creating pressure and heat before you actually separate the chip.
And that pressure triggers the hardening.
Exactly. You need a geometry that slices cleanly before the material even realizes what's happening.
That's a great setup. So let's look at the toolkit we have. The report breaks this down into managing a fundamental tension in machining physics, which is the trade-off between sharpness and strength.
This is the core dilemma of the whole field. You cannot have maximum sharpness and maximum strength simultaneously. It's physics.
Right, it's like a kitchen knife analogy.
Think about a razor blade. It's incredibly sharp, meaning it cuts with very little force, but the edge is microscopically thin.
So if you slam that razor blade into a hard rock...
It snaps immediately.
Versus, say, a splitting wedge or a meat cleaver. It's blunt, it's strong, it can take a beating, but you have to get it with a sledgehammer to get it to actually do anything.
Correct. In machining terms, we talk about this as the rake angle.
Rake angle, okay.
Yeah. Imagine a snow plow. If the blade is tilted back, scooping the snow up and away smoothly, that's a positive rake.
It flows easily.
Right, it's sharp.
Right.
But if the blade is standing straight up or even leaning forward into the snow, that's negative. It's scraping, It's pushing.
So positive is the scoop, negative is the bulldozer.
That's a great way to visualize it. And ISCAR's engineering is all about tuning that angle along with the edge preparation and the chip breaker to perfectly match whichever specific villain we're fighting that day.
All right, let's bring in the first villain then, heat. Specifically when we're dealing with titanium and those heat-resistant superalloys, the HRSAs.
Oh, these are arguably the most sophisticated enemies.
Yeah.
HRSA materials are designed for jet engines, gas turbines. Their entire job in the real world is to not melt when things get extremely hot.
Which creates a massive problem when you're trying to cut them and generate friction.
Exactly. It's the thermal conductivity issue.
Yeah.
Most metals, like your standard aluminum or mild steel, they act like heat sponges.
Meaning they absorb it.
Yes. You cut them, the cut gets hot, but the heat flows into the metal chip and the chip flies away. So the chip literally carries the heat out of the cutting zone.
But titanium is different.
Titanium is incredibly stubborn. It's a thermal insulator. It rejects the heat.
So it doesn't go into the chip.
No, it stays right there at the cutting interface. Right. It soaks directly into your tool. If you're cutting at high speed, you are effectively roasting the carbide.
So if we go back to our snowplow analogy, we absolutely cannot use the bulldozer here. The friction would just generate way too much heat.
Right. You need the sharpest scoop you can possibly get. You need high positive geometries.
To minimize the friction.
Exactly. You want to slice through the material with minimal resistance to generate as little heat as possible. And you need to do it quickly to avoid that work hardening we talked about earlier.
And this is where ISCAR introduces some really specific tech in the report, like the hilly turn system. The name implies a helix or a spiral shape. How does a spiral help with heat?
Well, think about jumping into a swimming pool. If you do a belly flop, you hit the water flat.
Ouch.
There's a massive impact all at once. In machining, a straight cutting edge hitting the metal flat creates radial force, basically pushing the tool violently away from the part, and it creates a huge amount of shock.
And a helix is more like a diver entering the water with pointed hands.
Precisely. The helical edge enters the cut progressively. It shears the metal gradually rather than slapping it all at once.
Which reduces those radial forces.
Significantly. Less force means less friction, which means less heat. The report notes they pair this with specific carbide grades like IC806 or IC907, which are chemically resistant to heat.
But the heli turn geometry is what stops the heat from generating in the first place.
Exactly. You're solving the problem before it starts.
The report also mentions something called notch sensitivity with titanium. That sounds like a structural weakness.
It is. Titanium is notoriously notch sensitive. If you nick the surface of it, it tends to crack or tear from that exact point, almost like a zipper opening up.
Wow. So a rough cut can literally cause the part to fail later in the field.
Yes. That's why ISCAR emphasizes vibration control here, too. They specifically mention their chatter-free geometries.
Because vibration leads to those little nicks and tears.
Right. Chatter is the absolute enemy of a good surface finish. If the tool is bouncing around, you're just hammering the part.
Which is bad for any metal, but fatal for titanium.
Exactly. So the geometry in their Logic 3 turn system, for example, specifically the LF3 and MF3 inserts, is designed to stabilize that cut.
The 3 refers to 3 cutting edges on the insert, right?
Yes, which is usually a challenge for stability in small spaces, but the geometry mathematically locks it in to prevent that harmonic vibration.
Okay, so for the heat-sensitive stuff, we basically act like a surgeon. Sharp, positive, slicing angles, super stable.
Yes.
Now let's pivot to a completely different problem. The gummy metals. Like stainless steel.
Stainless. Honestly, the most common headache in the modern machine shop.
I feel like everyone underestimates stainless because it's so ubiquitous. We see it in kitchen sinks, forks, everyday stuff. But machining it is a mess, isn't it?
It's a total mess. And the problem isn't just that it's hard, it's ductility. The material stretches before it actually cuts.
It's gummy.
Very gummy. When you peel a chip off, it doesn't want to snap and break away. It just wants to flow into this long, continuous ribbon.
The dreaded bird's nest. I've seen videos of this giant tangles of razor-sharp metal wrapping around the chuck or the tool post.
It's incredibly dangerous for the operator. And it destroys the part, too. If that ribbon whips around and hits the pristine surface you just finished cutting, you have to scrap the whole part.
So how do you fight that?
This is where chip control becomes the primary mission of the insert geometry.
Okay, so explain the physics of a chip breaker to us. I think people just imagine the tool cutting, but there's actually a whole micro landscape on top of the insert, right?
Yes, exactly. Think of the
Yeah.
top surface of the cutting tool as a miniature skate park.
A skate park.
Yeah, you have a cutting edge, but immediately behind it, there are ridges, bumps, slopes, and walls. That entire landscape is the chip breaker.
So the metal flows over the edge and immediately hits a ramp.
It hits an obstruction. The geometry physically forces the metal chip to curl tightly back on itself. You're mechanically overstressing that chip until it snaps.
So instead of a 10-foot ribbon whipping around,
You get thousands of tiny little 6 or 9 shaped chips that just fall harmlessly into the conveyor below.
and for stainless, the report recommends ISCAR geometries like the Logic Turn MF or Multi-Master.
Right. MF usually stands for medium finishing. You cannot use a flat tool here. The chip would just slide right across it.
It wouldn't break.
Nope. You need a geometry with a specific back wall to force that curl. But, and here's the catch, you still need a reasonably sharp edge because stainless creates what's called a built-up edge.
Oh, that's where the metal literally welds itself to the tool, right?
Yes. The gummy metal gets hot, gets sticky, and literally welds to the cutting edge. Then when it finally breaks away, it tears a microscopic piece of the carbide with it.
Like pulling strong tape off old paint.
Exactly like that. So ISCAR combines a sharp-ish positive rake to slice cleanly with a very aggressive chip breaker to snap the waste. It's a really delicate balancing act.
It seems like every material demands a totally different compromise. Which brings us to the heavyweights, hardened steels and abrasive cast iron.
All right, now we got to throw the surgeon mindset completely out the window.
No more scalpels.
None. If you took that sharp helical tool we use for titanium and touched it to hardened steel,
It would explode.
it would shatter instantly. The edge is just too fragile. Hardened steel resists penetration with immense, incredible force.
So we need the bulldozer.
We go back to the bulldozer. We need what they call reinforced cutting edges.
The report talks about edge honing and chamfering. This is the part that actually feels a bit counterintuitive to me. To cut the hardest stuff in the world, we actually dull the tool on purpose?
In a very specific, controlled way, yes. Think about a perfectly sharp point. It's a massive stress concentrator. All the force of that heavy machine is focused on a microscopic, atom-wide tip.
And that tip will just break under the pressure.
It has to break. So we apply a chamfer, which is a tiny, deliberately angled flat spot right at the very edge, or a hone, which rounds the edge off slightly.
So you're distributing that impact force over a wider, stronger area.
Exactly. You are protecting the brittle core of the carbide. We shift to negative or neutral rake angles. We aren't trying to slice smoothly anymore. We are literally shearing the metal off with brute compressive force.
The tool needs to be a fortress.
It has to be.
And this leads to what I think is the biggest aha moment in the entire report, the concept of hard turning.
Oh, this is a massive revolution in manufacturing.
Tell us about it.
Well, traditionally, if you had a steel shaft that was hardened to, say, 60 Rockwell C, which is extremely hard, you simply couldn't cut it on a standard lathe.
The tools couldn't survive it.
Right, you had to grind it, you'd use a spinning abrasive wheel and just slowly, painstakingly wear the metal down to the right size.
Which sounds incredibly slow
Yeah.
and messy
Yeah.
and requires a completely different, expensive machine.
Grinding is very expensive, it creates toxic sludge, and it really limits the complex shapes you can make.
But geometry changes that.
Yes. Because companies like ISCAR have developed these reinforced geometries, specifically when paired with grades like CBN or ceramic-coated carbides, we can now actually turn hardened steel on a lathe.
You're just peeling hardened steel like it's a soft potato?
Essentially, yes. Using robust geometries like the Logic Turn RM, manufacturers can entirely replace a slow grinding operation with a fast turning operation.
On the same machine they used for the soft turning beforehand.
Exactly. The throughput increase for a factory is massive. But it only works because that specific geometry directs the insane cutting forces into the thickest body of the tool, preventing that edge from snapping.
I love that. It's a huge productivity win that comes purely from understanding the microscopic physics of the edge.
Absolutely.
Now, I want to shift to a specific operation that the report highlights as being particularly dangerous, grooving and parting.
The part off. This is often the scariest 30 seconds of a machinist's day.
Why is that? Is it just because the finished part is about to physically detach and drop?
I mean, that's part of it, but it's really the claustrophobia of the cut itself.
Claustrophobia.
Yeah. In normal turning, you're usually cutting on the outside diameter of a cylinder. You have open air, open space for the chips to fly away.
Right.
But in grooving or parting off, you are driving a thin tool straight down into the solid material. It's full-width engagement. You have walls of solid metal on both sides of the insert.
So it's basically digging a tunnel.
It's a deep, narrow, fast-moving trench. And if a chip gets stuck in that trench, if it doesn't evacuate perfectly, it jams.
And the part is spinning at what, thousands of RPM?
Thousands. So if the chip jams, the tool snaps violently, the part gets gouged, or worse, things go flying.
So how does ISCAR's geometry solve the jamming problem? Because you can't just make the chip curl up like we did with stainless. You have to make it physically fit through the doorway of the trench.
That is the perfect way to put it. The geometries in their cut grip system, which are often labeled F, M, and R for finish, medium, and roughing, they manipulate the shape of the chip, not just the curl.
What do you mean by the shape?
They actually fold the chip along its length.
Wait, like folding a piece of paper in half so you can slide it into an envelope?
Exactly that. The geometry compresses the metal chip horizontally so that it is physically narrower than the groove it was just cut from.
That's genius.
It creates clearance on the sides so the high-pressure coolant can get in there and the folded chip can flush out without scraping the walls.
That is incredibly clever. You're physically modifying the waste product in real time so it doesn't kill the process.
It's essential, especially if you're grooving stainless steel. If you don't fold that chip, you're basically playing Russian roulette with your tool life.
We've covered a ton of ground here, from the heat-sensitive aerospace alloys to the brute force of the hardened steels. But the report concludes with a really important reminder. You can't just pick a geometry in a vacuum. There is an entire ecosystem of variables.
Context is everything. You cannot simply read the back of the box and say, oh, this insert is for stainless, so it will work perfectly.
You have to look at your machine. The report calls it the machine stability factor.
Right. Are you running this tool on a brand new 10-ton Swiss lathe that's bolted securely to the floor? Or are you on a 20-year-old machine that has a little bit of wear and slop in the spindle bearings?
How does the age or stability of the machine change your choice of geometry?
It changes everything. If your machine is older, or if the setup is less rigid, you generally want to lean towards positive geometries, the sharper ones.
Because they generate less cutting force.
Exactly. If you try to use a dull, heavy-duty bulldozer tool on a flimsy machine, the machine itself is going to push back. You'll get terrible vibration, bad tolerances, chatter.
But if you have an absolute beast of a machine,
then you can afford to use the stronger negative rake tools. You can prioritize tool life and run the machine much harder because the rigid frame can absorb all that punishment.
And coolant plays a big role in this ecosystem too, right? Specifically a high pressure.
A high pressure coolant, and we're talking 70 bar or more, is a massive force multiplier.
What does it actually do? Just cool it down more?
It cools, but it also acts mechanically. It can literally blast chips out of a deep groove that would normally jam. It can get right under the cutting edge and allow you to run a geometry faster than the catalog even says you should.
It widens the cutting window.
It widens the window significantly.
And that cutting window is really what modern manufacturers are desperately chasing, isn't it?
They are chasing predictability. That is the ultimate holy grail in manufacturing.
Not just speed.
No. Because an engineer doesn't want a tool that might last 100 parts, but might randomly break at 10 parts.
Because then you have to stand there and watch it all day.
Exactly. They want a tool that lasts exactly 50 parts every single time, without fail.
Predictability allows for automation. It allows you to actually walk away from the machine and let it run overnight.
Bingo. And that's exactly what these highly specific geometries provide. By tightly controlling the chip formation and the heat generation, ISCAR essentially removes the chaos from the machining process.
It's really a journey from chaos to control. I mean, we started this deep dive thinking about cutting metal as a simple contest of hardness, diamond versus wood.
Right.
But what we've learned is that it's actually a high-stakes, highly engineered game of physics.
It really is. I mean, we went from the heat-sensitive titanium, which absolutely demands a helical diving entry cut, to slice the metal without burning it.
All the way to the hardened steel, which requires a chamfered, blunt fortress of an edge just to shear the metal without shattering into dust.
And right in the middle, you've got the gummy stainless steel that literally needs to be tricked into breaking its own chips by a microscopic skate park geometry.
In every single case, the solution wasn't just make the tool harder. It was change the shape.
We are manipulating force vectors, heat flow, and material plasticity just by altering a cutting angle by a few tiny degrees.
It honestly changes how you look at the manufactured world around you.
It does for me, every day.
Next time you see a finely machined metal part, maybe it's the landing gear strut on the plane you're boarding, or a tiny screw in a pair of glasses, or a life-saving medical device, don't just think about the fancy metal it's made of.
Think about the negative space. Think about the specific tool that carved it out of the block.
Think about the exact shape of the edge that made it possible. Because if geometry dictates how we interact with the physical world so completely, it really makes you wonder, what other impossible materials are out there just waiting for us to invent the right shape to cut them?
That is exactly the question that keeps the R&D departments in this industry in business.
It's a fascinating thought to leave on. Thanks for diving deep with us today.
Always a pleasure.